Hi, this is part 3 of chapter 12. So we're gonna start where we left off previously. We're in section D, interpreting the results of a significant regression. And this is basically trying to say that, you need to be careful. Um, just because you did your t-test or your f-test and you found that the beta estimate is found to be statistically significant, that doesn't necessarily mean that X has an impact on Y. Or if you do find that the beta estimate is equal to 0, that also doesn't mean that beta does not have an impact on Y. Okay. The slope of the slope beta is estimated based on the sample of data, and this sample is not the whole population of data. Okay. Let me zoom in a little. In addition, there may be possible measurement error. Okay. So this can lead to false conclusions. Again, as I just stated, even if you rejected H naught, meaning you rejected the fact that the beta is equal to 0, it is possible that beta indeed is 0 and X has no effect on Y. Or opposite day is true. Even if you do not reject H naught, it is possible that beta does not equal to 0, or X does indeed have an effect on Y. Okay, and here's a simple example of issues that can arise. Fitting the wrong model. It may happen that Y and X are related, but in a non-linear way. Okay, specifically, let's suppose we have a range of X's, and here's the range of Y, and as X increases, Y increases initially, and after some time, Y falls as X continue to increase. So there's this like weird hump shape, okay? Or non-linear hump shape. But here's an issue. Suppose when you collect data to run the analysis to try to estimate beta, okay, you collect data from this region here. If you just collect data around here, you're going to estimate a line like line 1. No, as X increases, Y increases. Beta is positive. Suppose you got data from this region here, from D to F, or D to whatever this endpoint. If you do, you're going to estimate a downward sloping line. And then you would conclude that, well, beta is statistically significant and it's negative. So as X increases, Y falls. Lastly, what if you get data from C to D, or even the whole spectrum from A all the way down? And you assume that the relationship between X and Y is linear. So if you get this bubble right here, specifically from C to D, or even from A to F, you would just find a regression and find the slope to equal to 0, which indicates there's no linear relationship between Y and X. And you would say, oh, X has no impact on Y. X does not influence Y. But all of these would be untrue. X and Y is related, but not in a linear way, but in a non-linear way. Okay. So you do really have to be careful. Okay. Modeling is difficult, and some economists, many economists, when we create models, we do hundreds of models. Okay. Not thousands. Extrapolation. What is extrapolation? That's the next topic. Extrapolation is to apply the results of the model or linear regression analysis to values of X that are not included in the data or create the parameter estimate. So for example, in our model here, in our example in Excel, we use this data right here. Okay? We have students 1 through 10, and these are the scores. Okay. And it looks like math achievement score goes from, say, 21 all the way to 64. Oh, no, 75. Okay. So basically, extrapolation is okay, well, I use this data to create a model. What would happen if X was below 21 or above 75? Okay. So what if I had a X of 18? What would my Y be? Or what if I had an X of 79 or 83? What would my Y be? Okay. This is sometimes called forecasting or prediction. I think most of us would probably call this forecasting or prediction. Okay. Basically, you're using out of sample information to do some analysis. Well, this can lead to prediction errors. Okay, specifically, if we had this type of issue, we use data here to create this line, and we try to say, well, what if X was D? What would Y be? Well, if this is our estimated model, we would say Y would be all the way out here. But in fact, the true value Y is down here. Okay, we would be off by a significant amount. So if data from, okay, so that's what this is saying and this is saying here. Okay, so we need to be careful. Okay, and forecasting and prediction, um, that's going to add to more noise on top of just doing estimation with in-sample data. And we're going to learn that below in chapter 12. All right, let's go to causality. What is causality? Causality, the regression model provides correlation or linear relationship between X and Y. Okay. It does not provide any information on X causing Y or Y causing X. That is an assumption we made when we were using this data. Okay. But mathematics, which is the foundation of statistics, doesn't when we draw this model, or when we develop this model, y equals mx plus b model right here, there's no causality in this equation. It just says y and x is related, and the relationship is shown by a plus b x, whatever. Okay. So as x goes up by 1 unit, y, if b is positive, then y will go up by, if x goes up by 1 unit, we will also see y going up by b units. Okay. But it doesn't say anything about if x goes up by 1 unit, it causes y to go up by b units. Okay. That's something we put in to the math. Okay. And this idea of x causing y or y causing b, that is developed through our reliance on theories, common sense, and historical data analysis. Okay. We could run into a problem called reverse causality. Specifically, we think x causes y, but in fact, y causes x. Classic example that I always like to bring up is police and violent crimes. Okay. So let's go through this example. I think I've done it already, but let's do this. All right. So suppose we had a situation like this. Okay. And we collect data on the number of policemen, and we also collect data on number of violent crimes. Okay. And we just plot some data, and we find something like this, a positive relationship. If someone drew the graph this way or knew nothing about police and data, they would say, "Huh, as number of policemen increases, the number of violent crimes increases. Huh. So I guess if we get rid of all the policemen, that violent crimes would fall." Okay. But I think what just understanding police and violent crimes, etc., what these things are, it's not that the increasing number of police impacts the violent crime, number of violent crimes. It's not this, it's actually this way. As the number of violent crimes increases, that causes the city to hire more police. This is a classic example of reverse causality when we think X causes Y, when in fact Y causes X. We need to be careful of that. Another issue that can creep up is the omitted variable bias. That's something we talked about before, so I'm not going to go through it again. Okay. All right, let's move on. And let's go to section 4, diagnostic tools for checking the regression assumptions. Okay, we had some regression assumptions, and we're going to go through certain tools that exist for us to check whether these assumptions that we make to do our regression analysis are violated. Okay, all right. So let's go through the regression assumptions. Remember our relationship between y and x. Y is linearly related to x. We have y is equal to alpha plus beta x plus epsilon. Alpha, beta, and epsilon are the true values. They're the population parameters, okay? And we make some assumptions. We say epsilon is a random variable with mean 0, then on average should equal to 0, and a constant variance or standard deviation, meaning as x changes, this variance doesn't change, okay? Also, the value of E, or epsilon, is independent, okay? Meaning for some x1, student 1, okay, you have an error, it doesn't cause student 2's error to be a certain way. Student 1's error, student 2's error, student 7's error, student 10's error are all independent of each other, okay? The error term E is, there are ways to correct it. For example, let's say COVID occurred. That can cause all 10 students have some associated quote unquote error, okay, or something outside of math achievement scores and calculus scores that impacts the data. There are ways to fix that. That's again beyond this chapter. Okay, side note. That's a side note. The error term epsilon is normally distributed as well. So it's a normally distributed variable with mean 0, variance of sigma squared. Okay, so let's go through testing some of these assumptions. One is the dependence of the error term. And an issue here is that that's beyond the scope of this chapter. And effectively, this class, that's something you would learn in more advanced classes, but we'll just talk a little bit about it. There's something called, say, and specifically this exists in time series, but I've also just introduced one where you have some massive macroeconomic effect that influences everybody, okay? And that means everybody's errors are correlated. When you have these kind of issues, one of these dependent error term issue is when you play with, or I'm sorry, when you have time series data. What is time series data? It's when you have data collected through time at regular intervals, yearly, hourly data, daily, minute, seconds. Okay? For example, you have macroeconomic data of GDP every year that the federal government collects. Or some fancy dude at Wall Street collects Google stock prices by the minute, by the second, by the day. Okay. Every day he records Google stock price. This kind of data is time series data, particularly time series data of Google stock price per day through time, right? Or GDP through time. So it's time series data, and we collect it yearly or annually. When you collect data this way, you will have error terms, the epsilon, being dependent. Okay, meaning error term that exists in 2020 influences the error term that exists in 2021's data, influences the error term that exists in 2022's data. Okay. This results in a biased estimation of the model parameters. Okay. Basically, the error term assumption breaks down. That influences the estimate of alpha or A and the estimate of beta or B. Again, we have to rely on time series data methods. This is beyond this class, okay? But just a heads up. All right, let's go to some things we can do something about and check. One is residual plots. The first thing we're going to go through is residual plots. But before I introduce this, I'm going to go into our Excel file and do additional analysis that we haven't done already. Okay, so let's open it up and you will see it here. Okay, but we're going to assume that I didn't do it. I'm going to scroll out a little, delete, and we'll do it together. Oh, things apparently got erased. All right, that's okay. It's okay. We'll have to figure it out later. Okay, so let's go to data, data analysis, regression. Okay, so here's my regression input window for the Y's. Let's put in the Y's right here. For the X's. Oh no, I erased one of the X's. Oh no. And let's get out of here. Cancel. Oh no, I might have to. Let me see what the number is. Oh, there it is. It's back. Sorry. All right. Oopsie. Damn it. This is recorded. All right. Just skipped through this part of the recording. Sorry. Data analysis, regression. Okay. So you didn't see what I just happened. Input range. There. X input range. These thingamabobs. Click on label because we included the labels. Confidence interval, as I stated earlier, Microsoft Excel defaults with one confidence interval already, which is 95. If you want a second one to be calculated, you could define it here. Let's put 99. I want to do output range, and I'll put it right here. Okay. And let's see. Oops, sorry. And I'm going to click on all of these thingamabobs. We're going to go through most all of these. This. So what we're going to do right now is go through these thingamabobs right here. Press OK. And we have a regression output again. Okay, it's like the previous one we did down here. I'm going to do a bit of formatting because I'm oops, anal. Okay, let's I'm very organized. So times I like 0, 10. I hate all of these. Let's get like 4. Hate all of these. Get like, oh no. 4 significance, that's a percentage. Yeah. Oh my God, all of these. 4. These are percentages. These are not. 3, 4. Sure. Let's like, oh, it's because of these guys. Okay, all of these. Like 4. Oh, this dude. It's okay. Squeeze them. Okay. These guys. These dudes. Yeah. All right. Good enough. Good enough. All right. So we did that. And we have these. This one we're not going to talk about. We have these 3. Okay. So we did all the formatting and we kind of separated the pictures. Go back here like this. All right. Residual plot. Now we're back to residual plot. Other regressionist assumptions can be checked using residual plot. Okay. It's a plot of residual versus fit. Okay. Or X. Okay. Why do I say or X? Because the residual plot for is right here that Excel spits out, and it's different than the one that's actually discussed in our book. And it's different in the sense that the x-axis in the book is you should put the fitted y on the x-axis, while in the book, in Excel, they use x. They use, oh Jesus, x. They use x on the x-axis, okay? So fitted y for the book, and Excel uses x, but it's the same information, so don't worry about it. Basically, it's not what's presented in the x-axis that really matters. It's the shape of this, and really there's no difference, okay? So let's do this. So fitted y or x are measured on the x-axis, and the residuals, this is the residuals here, or the actual errors that are calculated, are measured on the y-axis. Remember, y hat, which is the fitted y, is equal to a estimated alpha plus b estimated beta times xi. So you could see y hat is just a linear transformation, or a linear, fancy way of saying linearly related to x. Okay, all you're doing is multiply by a constant and adding a constant. Okay, so all you're doing is is changing the placement here, just the scaling here, but the shape will be fairly similar of the plot. Okay, and this residual plot allows you to check for constant variance. Okay, it allows you to check for one of the assumptions, constant variance, and it allows you to check if indeed the relationship between y and x is linear. Okay? The plot should be free of any patterns. It should appear as a random scatter of points around 0. Around 0 on the y-axis, it should be a blob. And this is a reasonable one right here, because you have some down here, some up here, and it's basically around 0. Okay, with approximately the same vertical spread for all values of y hat, or in this case, x. Okay, so this is the residual plot, the same data that's residual plot, the math achievement score. This is the residual plot where you have fitted values on the x-axis, and this is the one where you have x on the x-axis, the math achievement score, and you could see the shaping is the same. This shows you how to output it, and we've already went through that. And this is what it should look like, okay? And this one right here, I found some pictures from online, put it into our notes. And this is similar to here, where you have the x measured on the x-axis and the residuals on the y-axis, okay? And you could see this is a good pattern where as x increases, okay, the residuals bounce around like a cloud around 0, okay? And they're all about the same distance away, negative and positive. Okay, that's what we're looking for. This is one bad one. And this one shows non-constant variance. As x increases, you could see the dispersion of the residual gets wider. So the variance here appears tighter or smaller than the variance as x is big. That's an indication that the assumption of constant variance is incorrect, and you're going to have to do something to correct for that. Here's another one that is, if you see, that's concerning. As x increases, you could see residuals start really high, positive, it goes down, and as x increases, the residual then goes up. This means that likely you have a nonlinear relationship between x and y. Okay? Okay. Let's move on. We're done with our residual plot. And now let's talk about the normal plot. So I'm going to put this thing, this one right here, put it up here. Okay. The normal plot is created from, if I click on it, from this output right here, this output table. Again, with all those new check boxes, we got this table here, we got this table here, and we got 3 pictures, 2 of which we're going to explain. And let's talk about the normal plot. Okay. Oh, okay. The normal probability plot, I've been calling it normal plot, graphs that plots the residuals against the expected value of that residual using the normal distribution. The plot should appear as a straight line sloping upward. This means the normal assumption is not violated. So basically, yeah, what I want you to do is look for whether all the dots are fairly linearly related, on a straight line and upward sloping. And that's what it looks like. Okay, that's what it looks like. You could see that the normal probability plot that is shown in the book is slightly different than the one that is shown in Excel. What Excel does is you could see percentage is on the x-axis, percent is on the y-axis here. So they flip the axes. The other thing they do is instead of plotting the residual, which I think makes more sense, Excel plots y. Okay. Now again, same information, it's been inversed, kind of flipped axes, but the goal is the same. Look at the picture. Does it all kind of fit on a straight line and upward sloping? It does. Good enough. Let's move on. Okay. If it doesn't, they don't look like this, they don't look like they're kind of on a straight line, then the normal probability assumption likely is being violated. Okay? All right, let's scroll. Let's get out of here and let's talk about, well, here I'm just explaining this. Okay, showing it the different variable and the flipped axes. Concept's the same. Must look like a straight line. Okay. Now let's talk about standardized residual and the associated plot. Now I don't have the associated plot here, but we'll talk about standardized residuals. The standardized residuals are shown here, okay? Right here. This is the table to the left, that get residual output table, okay? And here's the standardized residuals right here, okay? To calculate the standardized residuals, it's right here, the formula, okay? And what is the standardized residual? This is similar to the normal probability plot type of analysis, but it is standardized. So we're using the standard normal distribution and not the normal distribution to talk about the same thing, okay? All right, so remember when a random variable is standardized, we subtract the mean, divide by the standard deviation. So that's what we're basically doing here. Similarly, the standardized residual calculation is yi minus yi hat divided by s, the standard error, which is s of yi minus yi hat. Okay, standard error is s, the standard deviations, times the square root of 1 minus hi. What is hi? Hi is equal to 1 over n being the number of observation in the sample, in this case 10, plus xi minus xi bar. Let's scroll in so you guys can see that. Yeah. Xi minus xi bar. So each xi minus the average x divided by the sum of xi minus xi bar, okay? That's how you calculate it. Now, I'm not to test you on how to calculate this, but what I want you to come away from this is the following. The standardized residual, approximately 95% of them should be between -2 to 2. Then the normal distribution assumption is likely not violated. Here, if you look at the standardized residual, we see none of them are beyond 2 or -2. And that's what I want you to come away with this. When you do your analysis and you see a bunch of standardized residuals, see if about 95% are between -2 and 2. If that's the case, normal assumption is likely reasonable. All right, let's move on. Okay. Estimation versus prediction. Okay, let's go into that. Estimation versus prediction. And specifically, estimating y versus predicting y. Okay. Remember, we have this line of means. Expectation of yi is equal to, we expect each individual y to equal to alpha plus beta xi. Remember that we expect the error term. Here is the original model. I had it earlier up here. Let's go up. Oh, there it is. Y is equal to alpha plus beta x plus e. Epsilon. Epsilon has a mean of 0. So for any xi, we expect yi to be alpha plus beta xi and epsilon to be 0. Okay, that's our expectation. Scroll down. Okay. Okay. But when we have data, we don't know alpha and betas, so we estimate those. We're using A and B. Okay. So we don't know what the true line is. We only have an estimate of the true line. Okay. And with the estimate of A and B, we get yi hat. Okay. Yi hat is our modeled y given our estimate of alpha, which is A, and estimate of beta, which is B. Okay. So if we have some xi, we put in some x value, multiplied by B, and add an A, we get yi hat. Okay. So here it shows right here that we have a couple of issues here. One, we have the real relationship or the real the real relationship between X and Y. The light blue is the estimated relationship given that we have a sample of data. And so if we put in some X naught in, okay, so we put in some X into our estimated model, we would be right here. That's our Y hat for X naught. Let's suppose the actual value is up here, okay? This whole difference is E. Okay, E is being the actual error in estimation. That's our E. But E could be broken down into two components. One is epsilon, which is the difference between the true model, which we don't know, and the actual value. And this part here, which is the error in estimating the model. Okay? So we could break down the real error into two components. All right. So first, what we're going to do is talk about estimation and the standard error associated with estimating Y hat, estimating Y or Y hat. Okay, estimating Y, which is Y hat. So given we have some X naught, we plug it into our estimated model, we get Y hat naught. Okay, get this value here. Okay. This estimate Y hat has a standard error, has its own variance term. Okay, and that is this fancy thingamabob, which is the square root of MSE times 1 plus divided by n plus X naught, the number we put in for X, minus the average X squared divided by SXX. SXX is here, which is a sum of xi minus x bar squared. Okay. Now, most of the components in the formula we could pull from here. SXX cannot be pulled from this regression result that we have outputted. Let me show you this regret. Oh, let me show you a different. Okay. Maybe here. Okay. So this regression result right here that gets pulled out, spit out by Excel, doesn't explicitly show capital S, X, X. Okay. However, that can be obtained from the information here. Specifically, remember the standard error is equal to square root of MSE. Okay, what I mean by standard error, the standard error for B, okay, this right here, this number is equal to the square root of MSE, residual is this one, okay, divided by SXX. So if we just manipulate this, we could say SXX is equal to MSE divided by standard error squared. So we could actually obtain SXX without calculating this. Okay. And let's do it. Okay. So let's do this. So SXX, this is equal to MSE divided by standard error squared. So this dude to the squared. Make sure I don't screw this up. There. 2474. 2474. Okay. Well, if you scroll up and we calculated that right here. Okay. When we were trying to manually calculate instead of using Excel, we manually calculated A and B. As part of that process, we calculated SXX, which is XI minus X bar squared, and the sum of that was 2474. 2474. Okay. Okay, let's move on. All right. So if we were to do some analysis of y hat, like, you know, um, some hypothesis testing or building confidence interval, which is right here, we have we have a t statistic, the standard error. We have a t statistic, test statistic that's t distributed, what n minus 2 degrees of freedom, and the y hat, the y hat is t distributed. So we have a t statistic with n minus 2 degrees of freedom, and the t statistic is y hat minus expectational y divided by the standard error of y hat. Standard error y hat is this dude right here. Okay. Okay. And the confidence interval is always equal to, so the confidence interval when you're doing estimation is always equal to point plus or minus the margin of error. The point estimate is y hat. The margin of error is t of half an alpha times the standard error. It's always the same. Standard error of what? Y hat, which is, again, this gobbledygook of a mess. Okay. All right, so instead of doing estimation, if we choose to predict, we have another error that we need to account for. You choose to predict y rather than estimate, like out of sample prediction. X is equal to X. When X is equal to X naught, there's additional error in the prediction because of the deviation from Y from the line of means. Okay, so basically that's a fancy way of saying because our Y model, okay, I'm sorry, our model is not likely to be the true model relationship. Okay, A is not alpha, B is not beta. A and B are estimates of alpha and beta. And we need to account for that and the errors associated with that. Okay. All right. So how do we do that? Well, we had additional noise term. Okay. And so the standard error of y minus y hat is what we need to consider. Okay. Okay. And that is equal to the square root of MSC times the parentheses 1 plus 1 divided by n plus this gobbledygook x naught minus average x squared divided by SXX. The only difference between this and the standard error of y hat is this one doesn't have a 1 right here. Okay, this is MSC times 1 over square root of, 1 over n. This is MSC times the parentheses 1 plus 1 over n plus blah, blah, blah. Okay, so we have a 1 here. All right. Okay. The confidence interval for prediction, same, point plus or minus the margin of error. Point is y hat, same thing. Point, same thing, y hat. Margin of error is t of half an alpha times the standard error, and the standard error in this case is this gobbledygook. Okay. Okay. So here's a summary for estimation: y plus the margin of error, and it's this. For prediction, okay, y plus the margin of error, and again, the only difference is the standard error term. Okay. So what we're going to do next is the example, and I will do that in the next lecture. Have a good day.